For over 30 years, the Hubble Space Telescope has served as humanity's primary window into the deep universe. By capturing high-resolution images of distant galaxies and nebulae, it established the historical baseline for modern space exploration. However, Hubble operates with a specific physical limitation. Its sensors are designed primarily to see visible and ultraviolet light, the same narrow slice of the electromagnetic spectrum that our own eyes can detect. This creates a barrier when observing the origins of stars and planetary systems. These objects form inside dense, opaque clouds of gas and dust. Visible light cannot pass through this material. It is blocked and scattered by the dust. Because we relied on the visible spectrum, the formative years of the universe and the exact mechanics of star formation remained mostly invisible to us. To see further into the past, we have to look at the expansion of the universe itself. Light emitted 13.5 billion years ago travels through an expanding universe. As space expands, the light waves are physically stretched out, known as cosmological redshift. By the time this ancient light reaches us, it has stretched completely past the visible spectrum and into invisible infrared wavelengths. Catching this light required an observatory designed from the ground up to see in the infrared. Hubble's mirrors and sensors simply weren't built to detect these long, low-energy waves. Looking back 13.5 billion years meant engineers had to build a machine capable of mapping the invisible universe. Detecting those faint infrared signals requires two things: a massive collection area and extreme cold. The 6.5-meter primary mirror is made of 18 hexagonal beryllium segments that fold to fit inside a rocket. The gold plating on these mirrors is specifically chosen for its ability to reflect infrared light with near-perfect efficiency. The second requirement, extreme cold, is a matter of sensitivity. Infrared cameras detect heat. If the telescope's own hardware is warm, its heat radiation will overwhelm the faint signals coming from the early universe. To solve this, the telescope orbits 1.5 million kilometers away at the L2 Lagrange point, protected by a 5-layer Captain's sun shield. This shield keeps the instruments near absolute zero, even while the sun-facing side stays hot enough to boil water. For the mid-infrared instrument, passive cooling isn't enough. It uses an active cryocooler to drop below 7 Kelvin. These engineering requirements were the only way to physically see into the era when the first galaxies formed. While the mirrors capture the light, the instruments on board provide the analysis. The Space Telescope functions as a massive, high-resolution spectroscopy machine. A critical part of this system is the micro-shutter assembly on the NIRSpec instrument. It's a grid of nearly 250,000 microscopic, programmable doors. By commanding these tiny magnetic doors to open or close, the telescope can isolate the light from 100 different galaxies at once. This blocks out background noise, allowing the sensors to capture the distinct chemical spectra of every target. This assembly allows scientists to decode the chemical makeup of objects at the farthest reaches of the universe. In 2026, this hardware is producing a steady stream of data that is challenging our understanding of cosmic history. Researchers recently discovered JWST's quintet, a merger of 5 galaxies that occurred only 800 million years after the Big Bang. This discovery indicates that early galaxies grew and assembled much faster than our previous models predicted. The telescope has also produced high-resolution maps of dark matter, showing the invisible gravitational scaffolding that pulls regular matter together to build galaxies. Closer to home, the characterization of an object called 29 Cygni b, with 15 times the mass of Jupiter, is helping astronomers define the specific mass boundary between massive planets and small stars. From local exoplanets to distant galaxy clusters, this access to infrared light has forced a re-evaluation of how the universe evolved. This focus on data is reflected in how the telescope is used. In its 5th cycle of operations, 80% of its observation time is dedicated to spectroscopy rather than standard imaging. This marks a shift toward deciphering the chemical fingerprints of the universe. We are now gathering the data needed to analyze the composition of the earliest objects in space. By bypassing the physical limits of visible light, the James Webb Space Telescope provides the information required to understand the transition from the Big Bang to the modern cosmos.